I am Sunira from Department of Physics, Government College, Madapalli. In this lecture, we will learn about integral calculus. Okay, so as all of you know, this paper electrodynamics requires so many mathematical tools. We learned about some of them, vectors and vector calculus, all that things. Now, we want to discuss this integral calculus. There are many types of integrals. We mainly discuss only three types: the line integral, the surface integral, and the volume integral. Okay? So, integrals. The first one is line or path integral. The second one is surface integral. This is also known as flux. Surface integral also known as flux. The third one is called volume integral. Volume integral. Okay. Actually, in this case, the first case, the line integral is along a line. Okay. Along a line. In this case, this integral is over a surface. So it is called surface integral over a surface. Then comes volume integral. This integral is over volume. Okay. So there are three types of integrals we want to learn now. The first one is line integral. This integration is along a line. The second one is surface integral. The surface integral is over a surface. The third one is the volume integral. Integration over a volume. Okay, so we want to learn all these things now. So as the first case, we will learn about this line integral. Okay, line integral. Line integral. So, as we already discussed, this line integral is integration along a line. Here, our function is a vector function and the integration is along infinitesimal displacement vector. Okay, you learned about many types of integrals earlier. Here we discussed the integration of a vector function along infinitesimal displacement vector. It is called the line integral. So here we define this line integral as integral a to b vector v dot dl. This is the definition for the line integral, which runs from a to b. Okay, so where in this vector v is a vector function. Vector v is a vector function. Vector dl, we learned about dl earlier. Vector dl is the infinite displacement vector. Okay, infinitesimal displacement vector. Displacement vector, infinitesimal displacement vector. Okay, so the line integral is defined as integral a to b v dot dl. Here there is a dot product. The two quantities here are vectors. This is vector function and this is the infinitesimal displacement vector. This integral is called line integral. So, what is peculiarity of this integral? This integral is running over a particular path. Okay, this integral is running over a particular path which connects the points A and B. Okay, so I will show you here the peculiarity of this integral. For example, we can draw, I draw here a YZ plane. Let it be, this is the YZ plane. Okay, here there is 2 points A and B. We want to integrate the vector V along this line A to B. Okay. Now, which is the path we want to integrate? That is the question. As you know, there are infinite paths connecting these 2 points. I will show you 3 of them, 3 or 4. Okay. See, this is the one of the line, a straight line. This is one of the paths connecting A and B. If you find out this integral A to B V dot dl along this line, you get an integral. Okay. Now you want to take another one. Suppose this is your new path. Okay. This is your new path. Here also you can find out this line integration over this path. Okay. So I can show you here. Suppose this is the path 1 P1. This is the path 2 P2. Okay. Now there is another path P3 like this. Okay. This is P3. So all these P1, P2 and P3, all these are different paths connecting the points A and B. Okay, so if you take the line integral over this path, this is different from this path P2 and this is different from the third path P3. Okay, that means the line integral defined here depends on the path connecting the 2 points. Okay, the line integral. Okay, line integral depends on paths connecting A and B. Path connecting A and B. Okay, so the line integral depends on paths connecting A and B. If you take the integration along this direction P1, this integral is different from P2 and these two are different from P3, etc. This is the peculiarity of a line integral. In general, line integrals differ from one path to another. But there is a special class of functions such that they can depend only on the endpoints. Okay, so note the point. This is the general condition, but there is a special class of functions. There is a special class of functions. There is a class of functions which depends only on endpoints. Okay, so if your function is included in this special category, then if you find out the integral along P1, that's equal to along P2, that is equal to along P3, etc. Do you get the point? Okay, that means the line integral is defined as the dot product of vector function along the infinitesimal displacement and integration along the infinitesimal displacement. Okay, that is the definition for line integral. This line integral depends on the path connecting the two points A and B. In general, if you find out along P1, the integration along P1, this value is different from the value along P2. This is different from value along P3. This is the general case. But in the case of certain functions, certain class or special class of functions, its line integral depends only on the endpoints of integration, that is A and B. Then what happens? Then if you find out the integration over any these types of path, you will get the same result. Okay? The example for this type of a vector function is conservative force. In your second semester, you learned about conservative force. Okay? So, here the conservative force includes in this special class. Okay? Example, conservative force. Conservative force. Okay. One more thing, you can find out an application in this section itself. The famous line integral is the work done. Okay, work done is a famous line integral, because if you want to find out work done, you have to integrate force A to B F dot dl. This gives you work done. Okay, this is an example for line integral, work done. Work done is an example for line integral. Integral A to B F dot dl. Here F represents the force. Okay, if this integral is independent of the path connecting A and B, then this force is called conservative force. Okay, so remember all these things in connection with the line integral. The first point is line integral is defined over an displacement vector. Okay, a vector function taking dot product with the infinitesimal displacement vector and the integration over it gives you the line integral. Okay, similarly, the line integral or the path integral depends on the path connecting the two points A and B. In general, line integral depends on the path connecting the two points A and B. Okay, at the same time, there is a special class of functions. Functions means V. There is a special class of vector functions V, such that their line integral depends only on the endpoints. Okay, only on A and B. Then what happens? It is independent of the path chosen from A to B. Okay, in that case, you can define a conservative force. One of the famous line integral is the work done, which is defined as A to B F dot dl. Here dl is the infinitesimal displacement vector. This vector F represents the force. If this work done depends only on the endpoints, or it is independent of the path connecting A and B, this force is called conservative force. Okay? So, in connection with the line integral, please remember all these things. We need it later in this paper. Okay? Now, we can do a problem to check how to evaluate this line integral. Now, we can do this problem. The problem is calculate the line integral of the function v equal to y square x cap plus 2x y plus 1 y cap from the point a equal to 1 1 0 to b equal to 2 2 0 along the paths 1 and 2. What is integral v dot dl from a to b along path 1 and returns to a along 2? Okay, so this is the problem. In this problem there is a figure given. In this figure, the figure is shown in the xy plane. As you see, your function has only x cap and y cap. So the vector function lies in the xy plane. Okay, similarly it is given that a is given by 1 1 0. 1 1 0. X coordinate 1, y coordinate 1. There is no coordinate for z. So 1 1 0. A equal to 1 1 0 and B equal to 2 2 0. Because these points lie in the xy plane. So z equal to 0. Okay, these are the 2 points A and B. Now it is given there are 2 paths connecting the points A and B. The first one is this path. Path 1 is given as this one, A to B, like this. Path 2 is given as like this. In this figure, this one shows you the path 1 and this one path 2. Okay, so there is 2 paths connecting these 2 points. 2 paths are given. Okay, now we want to find out the integral v dot dl. V is given here. Okay, integral v dot dl along a closed path. Okay, along a closed path. So I can write here. You want to find out integral v dot dl. Okay, what is the meaning of this one? This closed circle. This circle represents a closed line or loop. Okay, this one represents a loop. This one represents a loop. So integration over a loop is shown here. Okay, so you have to find out integration from A to B and B to A. That is given here. Okay, from A to B along 1. So A to B, you have to select this path, path 1, and returns to along 2. Returns to A from B to A along 2. Okay, so here we have to find out integral A to B v dot dl along path 1 and this plus integral this one this time. Actually this is minus integral A to B along path 2 because I show here A to B. You need B to A. So I put it here as minus sign. Integral A to B along path 2 vector v dot dl. This is equal to closed loop v dot dl. Okay, I think now you clear the problem. What you want to do? There is given a vector function which lies in the xy plane. How can you decide this thing? Because you have here x component and y component. So this vector function lies in xy plane. There is no z component here. Okay, so in this plot also, in this curve diagram also, we shows only xy plane. Now it is given that the point A equal to 1 1 0. So this point is lying x1 y1 and z0, 1, 1, 0, and the point B at 2, 2, 0. Now there are two paths connecting these 2 points, path 1 and path 2. Okay, path 1 is like this, path 2 is like this. But you want to find out the integration over a closed loop. Okay, integration over a closed loop. This is the integral. Integral V dot dl. How do you get this? Integral A to B along path 1 V dot dl plus integral B to A along path 2. That is what we have written here. Integral A to B V dot dl along path 1 minus integral A to B V dot dl along path 2. So you goes from A to B like this and returns from like this. From B to A like this path 2. So altogether it gives you a closed loop. Closed loop V dot dl. Okay. Now the problem is clear to you. I think we can solve now. So I just want to erase this question part. Okay, now I can write the functions here. It is given that vector v equal to y square, vector v equal to y square x cap plus 2x y plus 1 y cap. Okay, the function is this one. Okay, so the given vector v is given that y square x cap plus 2x y plus 1 y cap. Now first we can find out along path 1. Path 1. Okay, along path 1. In this case there are two segments along this horizontal line and along this vertical line. The integration along the horizontal line is represented by this one. Okay, so here along this line, what is dl? dl equal to, what is dl? dl equal to dx x cap, right? dl equal to dx x cap, because this is parallel to x axis or along x direction. So dy equal to 0. We already found that this thing is lying in the xy plane. So there is no dz. dz is also 0. Okay, so along this direction, this one, along this one, dl is given by dx x cap. Okay, so v dot dl equal to, what is v dot dl? v dot dl equal to, this one is v dot dl is along x cap, so we have only x components. Taking dot product, you have only x components, so you get here y square dx. v dot dl equal to y square dx. Now we want to integrate this one, but you know that along this line, what is y? Along this line, what is y? Y is 1. Okay, this is 1. Along this line, y equal to 1. So here y equal to 1. So what happens? v dot dl equal to dx. Okay, so we have to integrate x equal to 1 to x equal to 2. Okay, this is the lower limit. Here the lower limit is 1 and the upper limit is 2. So x equal to 1 to 2. Okay, So now we can integrate this one. Integral 1 to 2 v dot dl. V dot dl. This is equal to integral 1 to 2 dx. Okay, if you integrate this, you get x from 1 to 2. Okay, that means this is equal to 1. Okay, so integration along this horizontal line gives 1. Is this path 1 is finished? No, because there is one more component. If you have to find out the vertical line integral also, this part also, then only you reach at B. Now you start from A and reach it here only, not here. Okay, so we want to integrate from this point to this point. This is along the y-axis. Okay, so here next step I show you the second part. This one. Okay, along this. So along this direction, what is dl? dl is along this direction, so dy y cap, right? dy y cap. So v dot dl equal to v dot dl. So you have only y cap components, so you get 2x into y plus 1 dy. Okay, 2x into y plus 1 dy. Now along this direction, y varies from here to here, but x is constant. What is x? X is this 2. Okay, y varies from 1 to 2. Y varies from 1 to 2, but x is a constant. This is given by 2. So along this line, x equal to 2. You can substitute here, so you get integral 1 to 2, 1 to 2, 1 to 2. Okay, integral 1 to 2, 4 into y plus 1 dy. Okay, 4 into y plus 1 dy. What is this 4 into y plus 1 dy? This is equal to 4 into y square by 2 plus y limit 1 to 2. Okay, so you get here 4 into what you get here, 2 square, 4 by 2, 2, here also 2, 2 plus 2, 4 minus 1 by 2 plus again 1 by 2 minus 1. Okay, right? So here you get minus 3 by 2. So 4 minus 3 by 2. That means you got here 8 minus 3 by 2. Okay, 10. Right? You get here 10. So in this part, along this part, you get 10. Now, what is this integral along path 1? So, you get the integral along path 1. The integral along path 1. Integral a to b along path 1 v dot dl equal to, along this one, this is given as 1. So, 1 plus along this part. This is given as 10. So you get total 11. Okay. So integration of this vector function along the path 1 is obtained as 11. Okay. Is our problem finished? No, it is not finished. Why? Because we want to find out integration of this function along this line, path 2. Okay. So, as a second part, we can find out the integration along this path 2. Okay. So, this is V. Now, we want to find out integral A to B along path 2 V dot dA. Okay, so you know that this A is 110, B is 220. So what is the connection between this x and y along this line? This is the straight line, and from the expression 110 and 220, you can find out that here along the path 2. Along path 2, x equal to y. Okay, along path 2, x equal to y. Similarly, dl equal to dx x cap plus dy y cap. Right? But from this relation, x equal to y, you can see that dx equal to dy. Okay, from x equal to y, you get that dx equal to dy. You can use the relation here. So you got dx x cap plus dx y cap. Okay, now you can take dot product with this vector v. So you get integral a to b vector v dot dl. This is equal to, and you get x cap dot x cap. You get y square dx. Okay. First thing, I just write you v dot dl. Then we write the integral. So if you take the dot product, you get y square dx. Okay. Y square dx plus 2x into y plus 1 dx. Right? Okay. Now we can use this relation also here. Then we have only one function, one integral. You can use this relation x equal to y. Substituting here for y, you get here x square dx plus. Here also you can substitute x. So 2x x plus 1 dx. Okay. Now you can integration is over only on dx. So you have integral v dot dl only over integration was dx. Integration over dx. So dx varies from 1 to 2. From you start from here x coordinate is 1. When you reach here, your x coordinate is 2. So x varies from 1 to 2. Okay, this gives you the integral a to b v dot dl along the path 2. You can integrate now this thing. You get here the first part, you get here x cube by 3 varying from 1 to 2, x cube by 3, this plus, then here 2 into again x cube by 3 plus x square by 2, limits varying from 1 to 2. 8 by 3 minus 1 by 3 plus 2 into 8 by 3 plus 4 by 2 minus 1 by 3 minus 1 by 2. So what you get here? Here 7 by 3. When it comes here, you have 2 here, 3 by 2. You can simplify all these things. Then you get 10. You get here 7 by 3 plus 2 into 7 by 3 again 8 by 3 minus 1 by 3 7 by 3, then plus 2 minus 1 by 2 3 by 2 like this. Once you simplify this, you get here, and you get here 6 here. So altogether you have 7 by 3 plus, but you get here simplifying, put here 6, so cancelling out, you have 2 into 14 plus 9 by 6, so here 3, so you have 10. Okay, so this integral gives you 10. Now what you get, I can conclude the result here. Okay, now you get integration over part 2 from A to B gives you 10. Okay, integration from A to B gives you 10. Integration from A to B along path 1 gives you 11. So what we can conclude from here, if you take different paths connecting the 2 points, you may get different values for the integral. In general, the integral, line integral, depends on the path connecting between them. Okay, now our problem is not finished. We have to find out the closed integral. Okay, so I can write the two results together here. As the integration over the path 1 gives us integral A to B along path 1 v dot dl gives us 11. Okay, similarly integral A to B along path 2 v dot dl gives us 10. Okay, now we need the integral, closed integral. If you put here closed integral, there is no meaning to put upper and lower limit. We start from a point and end in the same point. Okay, so just put like this. This means start from A and return back to A. Okay, so you start from A along this path 1. So this v dot dl equal to, you start from A to B along path 1. This gives you integration as 11. Okay, then when you reach here, you return to A along path 2. Okay, So, hope that you understand how to find out a line integral or path integral. So, I can wind up now. I think you understand the problem very well. Here we shows it is given a vector function here, and we want to find out line integral along two different paths. We find out the line integrals along two different paths. Then we combine them such that it forms a closed loop. Okay, that is what we have done here. Then you get the integral value as 1. Okay, so we can conclude now. The fact is that line integral is defined over an infinitesimal displacement vector. Okay, and the line integral depends on the paths connecting the 2 points. Certain class of functions are independent of this path chosen. In that case, the line integral depends only on the endpoints. Okay, so you remember all these things, then learn well. We need all these things later to learn this electrodynamics. Thank you.